This is a production of Cornell University.
So, waste not, want not, which is a great saying, of course, and as you appreciate with many spraying applications, there's quite a lot of waste, as I'll show you. And so I was particularly asked to talk about recent advances in technology, particularly then towards precision farming. As you realize, there's a great movement in the world towards the precise application of all inputs into farming, and in certain cases the outputs. And so I'd like to share with you the work that we've done here at Cornell. I'd like to acknowledge the help of my three most recent postdocs. Jordi Lawrence and Tomás Pelea are both from Spain and have now gone back and have good jobs in Spain. And Chung Yuan was from China, is now currently working here in the US at another university. My group at Cornell are charged with looking at pesticide application technology as a way of improving spraying via engineering methods. We do this in three distinct areas: test new sprayers, new spraying ideas, develop methods for our growers. I've worked particularly with fruit and vegetable growers. The fruit growers in particular, as you'll see, use a machine that blows spray all over the place, so we have a lot of waste, hence the title of this talk. And so we develop ways of improving deposition and reducing drift. And finally, because I have a 60% extension position, we do a lot of extension demonstrations, both here in the US and around the world. I've just come back from Australia and Europe, where I've been speaking to grape growers, and I'll leave again on Monday to talk to avocado growers in Mexico. And as I've never yet seen an avocado tree, I think Monday is going to be a very steep learning curve, and the 2 days of touring around to see the trees. But to many people, a sprayer is a sprayer is a sprayer. That, as you'll see, is not quite true. But in all cases, no matter which audience I'm speaking to, our challenge is to produce quality food and drink for the consumer or for the livestock that we're about to feed. In the case of the consumer, then disease and insect-free and blemish-free, of course. The challenge to the farmer or grower is to improve the spray deposition throughout the canopy. And when I work with fruit crops, you will appreciate, for example, in citrus, that's quite a challenge when you look at citrus trees. Primarily in New York State, of course, it's apples and grapes, apple trees and grapevines. And it still remains a challenge to improve deposition throughout the canopy. And a lot of our work has been done on that, as I'll show you. And reducing drift is the other big issue. Society doesn't care for drift. We don't want drift in our waterways, our water supply. And of course, where we have all these wineries here in the Finger Lakes, on Long Island, etc., it's this type of thing which affects the public profile of agriculture in the world and the public's perception of what we're doing. And this photo is from the Hudson Valley, from a vineyard, and you can see this tractor should be green. This one here is from a place fairly close to here, and again that should be green. People who buy John Deere pay a lot of money for that green paint, and to cover it here in diphane and here in surround is a very poor image to give to the buying customer coming to your winery or your fruit stand. So I'd like to split my talk into two main areas. One is the work that we've done up at Geneva, and the second is examples of boom sprayer work that other people have done. Spraying is simple. Everybody will tell you that. You just get a sprayer out the barn and fill water and product, your pesticide, put it in, and off you go. Well, I've made a 40-year career trying to complicate what is a simple process. And as you'll see, we've developed it into the volumes of air and liquid. So there are two, in fruit spraying, there are two distinct categories, two fluids, air and liquid. And so in the last 7 or 8 years, we've concentrated with the three postdocs I mentioned on trying to measure the airflow, monitor the airflow, in one way or another and then adjust the airflow, equally changing the amount of liquid that's being applied. This is the classic sprayer count. This work was created by Santiago planners over in Catalonia, near Barcelona, in the town of Lleida University, and has stood the test of time. You see, it's a very old piece of work. Hasn't changed. In New York in particular, well, the whole of the US, we use sprayers like this to spray trees, apple trees and grapevines. In the world, probably 95% sprayers are still like this for fruits, and you can clearly see at whatever application rate. You can read as well as I can, so I tend not to repeat what you can see on the slide, but you can clearly see that at the very low application rates, 10 gallons per acre, then you use a very, very fine nozzle, which leads to a lot of drift. And so when we're looking at the red symbols, only 54% is going in the canopy, 45% is drifting away. And if ever you go around a vineyard or an orchard in the spring, you will see this. When there's very little leaf to intercept the spray, very little canopy, there's a tremendous amount of drift. And at best, and as I say, this work has stood, lots and lots of other people have tried, repeated Santiago Planas' work, and this stood the test of time. At best, we're only getting 75% in the canopy. This, to anyone, is appalling. It's a waste of product, it's bad for the environment, and from the farmer's point of view is economically, it's just crass stupidity to be wasting so much money. And so it begs the question, is this the best we can do? Is this precision spraying? The other thing that's happened, orchards, if you're not familiar with the modern system, we have more trees per acre. We're looking maybe anywhere between 700 and 2,500 trees per acre. Huge hedge-like structures, very close together, 10, 11 feet apart between the rows, and the trees now are very well manicured, just like vineyards, compared to the photo on the right, which, as you can see, is the traditional orchard. And the growers still use the same air sprayers based on 1960s technology. And so, as I'm one of the only people working in this area in the US, then there's quite a good challenge, and of course a very good access to research dollars, as you will see. So I have very little competition in this field here. So our dream has been, for the last decade, to create a fully automatic sprayer, and that's the basis to my talk. We first of all look at our target, whatever that might be. Is it the leaf? Is it the disease? Is it the fruit? Is it the insect? Whatever it is. In relation to the growing canopy, like all plants, early season versus late season, full canopy. We do this with an array of sensors, which I'll show you. We've tried different types. We put it through a processing machine, and then we adjust the two fluids, the liquid flow and the air flow, because in fruit canopies we need air to help penetrate these dense canopies. So the controller is the smart box in the middle, obviously, and that's what my postdocs have been extremely good at creating, the software. And as I say, the sensors recognize the canopy, and then we make adjustments on the move. GPS, then everyone knows about GPS. You have it on your phone, on car, road maps, stuff like that these days, so I won't dwell on that, but it does give us our location. So this is old hat, as you know, GPS, and it gives us exactly where we are. What we've done at Geneva, we've fitted an array of sensors on a sprayer. This is a vineyard, a variety Vigneault, French hybrid, and you can see as the tractor goes through the row, then the sensors are sending out a sound wave. So we're using ultrasonics, to send out a sound wave. Notice the white envelope is wider than the row of grapes. We also do the same in orchards. Here's the modern orchard system. Very narrow canopy, a manicured canopy, just like the grapes, and a wider envelope than the actual canopy width. Okay? So we're using sound. As you know, sound can be generated by using a magnet in a coil. So we can, the loudspeaker is the example that we're all familiar with, and we hear this sound, the sound wave. We can record sound by sending it back to a pickup, to a microphone, as you can see, or in effect the loudspeaker. And as the magnet moves back, it now sends us a signal. Here is the trace from a typical sound wave over time. So we have a signal in voltage and a time frame in seconds. We're using ultrasonics. Ultrasound then is at a higher frequency. Can you see 2 megahertz? Between 20 kilohertz and 2 meg is the sound area, or area of the sound wave that we're picking up. Okay? It works simply by sending out a sound wave, and then it receives the echo. And the highest voltage signal we receive is our peak. So when we set up our equipment, we set it against a wall. This is a solid, if density of canopy is our interest, then the wall is solid, so that's 100% dense, as you'll appreciate. And so our sound wave gives us this voltage in our machine, and then anything less than that would obviously be a less dense or a sparser canopy. This is the system we use. You'll see in a moment. Here it is. As the tractor goes down the row, as I showed you in the video, we're measuring the sound waves coming back. Depending where it is within the canopy, we're getting different peaks according to the density of the canopy. And so when we total the peaks together, we get a certain value. That value is represented in volts. Okay. In 2014, we had a look at this and thought this, well, earlier than that we started work, but in the first published results were based on the 2014 season. And you can see here we have the date, 21st of May, right through till the 19th of August. Notice then every week we go to the orchard or the vineyard and measure the canopy. And we were looking for what we estimated as density. And we called it ED, estimated density, in those days. We would look at both sides of the canopy, left and right, or east and west, and then the dotted line is the average. And so the first thing we noticed then, as the density changed, as the canopy got heavier as the season progressed, therefore we were getting a different signal, voltage again. So this was really, really good. But like all good research, at the end of July, due to the vagaries of the New York weather, we got a hailstorm came through, a severe hailstorm, and that was here. And it only came to the experiment station at Geneva, didn't hit any of our neighbouring farms, and it decimated everybody's field trials. All my colleagues with apples, everybody, all the grapes, they were just hit by big hailstones, and all the fruit was perished. It just went, no good. So that's the date of the hailstorm, yeah, end of July. We then went to the field. About 10 days later, we were also devastated by this, and we noticed that our signal was lower because all the leaves were shredded, so our density had changed. And so there you can see it in the orchard. In the vineyard, they then wanted to save what little fruit was left, and so they net the canopy, net the vines, which is in this shaded area. And because they then gather the vine leaves together, our density signal went back up. So we thought, this is jolly interesting, but we hadn't compared it with real density measurements that our colleagues in horticulture use. So we asked colleagues like Alan Laxo, how do you actually measure density as a horticulturalist? And they use a system called PQA. And PQA involves thrusting a pole into the canopy, and you count every time the pole, or stick, bamboo cane in this case, every time the bamboo cane touches a leaf or touches the fruit. And you get a number. And as engineers, we wanted to repeat this performance, so we created a small frame. Every week, one of our Cornell summer scholars went out throughout the whole of the growing season and put in the stick with the PQA, here it is, and would count the number of leaves. This is a very simple system and was developed by a man called Richard Smart, who was a grad student here and has gone on to become a very famous viticulturalist. Anyway, it's an acceptable practice. It was acceptable enough to get it published, so it's pretty good. So we're quite happy. And so you can see as the season went by, as the leaves filled, our PQA went up. Equally, look at our signal in voltage from our sensors. So this is in grapevine, Cabernet Franc, or Franc, you're familiar with that. And so you can see that when we lay the one against the other, PQA against voltage, what a wonderful graph. What a wonderful end to a great career, you might say, that we've finally got something that looks as good as that. And we did the same with apple trees, and we've done it with a number of different varieties of grapes and a number of varieties of apples, because this project in particular was funded by apple and grape industry. What can we do, though, from a spraying point of view? We now know there's a signal, a voltage, from the sensors, from the ultrasound sensor, giving us a number. How do we then relate that to the sprayer? How do we make real-time changes as we're driving along? So remember, there are two fluids, the liquid and the air. In both cases, we have demonstrations to show you how we can change a liquid using a Leckler Vario Select nozzle or a capstan nozzle, and the airflow by a system we've patented here at Cornell to adjust the airflow, or using Australian fan system called Sardi fans. So we'll start off with liquid. The first system we looked into was the use of pulse width technology, PWT. Those of you who are familiar with a bubble jet ink printer, which I know many students aren't, because it's old hat really, bubble jet ink printers, but the idea was to have a small valve which went up and down rapidly and would fire dots of ink at your paper and create the letter or the font, whatever. The same principle was developed into a spray nozzle by other researchers, and depending, it's simply a little valve, really like a solenoid valve. So you apply a current to the valve, and the valve will get lifted. And so in this case, the valve is up here. When the valve is lifted, the liquid can flow out through the nozzle. If you have a long current, you get a longer lift, and therefore more spray goes out. If you only open the valve for a short time, you get a very small amount going out. And as I'll show you in the next video, this gives us a pulsing effect to the spray nozzle. And so some of you will remember years ago there was a specialty crop research initiative which still goes on, and the federal government gave boatloads of money to some of us, and we teamed up with Carnegie Mellon at the Robotics Institute, University of Florida, because we were working with citrus, and at Cornell we developed the sprayer part to go along with this device. And so let's have a look at that. And this was to develop an autonomous, fully autonomous tractor and sprayer. And there it is. There's a classic air blast sprayer, and you'll be able to see the tractor will move through the orange grove completely without anyone driving it. It's fully autonomous, and it will change the amount of spray according to the size of the citrus tree. See, no one's driving it. In Florida, they have a thing called greening disease that's spread by a psyllid, which is a little insect. Spreads is devastating their industry, and so they were particularly interested in this, because they have replant trees, a little tree that may be 3 feet tall, very sparse, and then a very, very dense machine. So that we're monitoring the canopy. Okay? We're monitoring the canopy and then creating a map of the different sized trees. The algorithm then changes the signal that goes to the pulse width nozzles. Can you see them pulsing? All the time. And see, here are small trees. You'll see every now and then tiny trees and then these very dense orange trees. If there's a gap, it switches off. There's some little trees, do you see? They might only want a teaspoonful of spray and a small amount of air, whereas this will want 3 bucketfuls of spray and a lot of air to blast the spray in. Okay? And so there it is. We've had a huge grant, nearly $5 million. So everyone was quite happy. So we did that. The problem is it's too sophisticated for most growers. You know, it's a very nice system. It, you know, a lot of brain power into it, but it's too sophisticated. So in New York, not that our growers are not sophisticated, anything but we wanted to develop a simpler system. So here's a sprayer that was given to us by a company. Here's the tall mast with the ultrasonic sensors on it. This is the worst photo you've seen. Ignore all these wires. Now that I've drawn attention to them, you look at them, but they shouldn't really be there. And so here it is. It's a tower sprayer, and attached to the system is an air compressor and electric valves. And what we're going to do is use air to open or close these valves. Let's have a look at this. Here we are. What we've chosen is a Lechler, which is a German nozzle assembly, the Lechler Vario Select. So instead of having the little pulse width nozzles pulsing, wearing themselves out, this is a standard nozzle that all the growers were familiar with, or are familiar with, and now we have a nest of them, 3 of them in a small cluster. And so by opening or closing an individual nozzle or any combination of nozzles, we can get a different flow rate. And so here we have the different pressures that they might operate at. If we open just an orange nozzle, we'd get a flow rate of about 9 litres a minute, as you can see there. If we open the green nozzle, we'd get about 11 or 12 litres a minute. And then if we operate the yellow, we will get about 16 litres a minute. So by having a cluster of 3 nozzles, we get a variation in flow rate. But look, if we have a combination, orange and green, orange and yellow, so on and so forth, green and yellow, and then all 3 of them on. So you can see by having this system, which is very simple, it's just operated in our case by air, can also be operated electrically, and so we can go from about 9 litres per minute all the way up to 38 litres just by switching on different nozzles, as I'll show you, and at different pressures. So you can change pressure and therefore you get that. Let me just show you this at work, and we'll come back to the graph. Here are the nozzles. This is a sensor. This is in our lab. As the sensor moves towards the black board, which is representing the canopy, so the closer we get to the canopy, then the different nozzles switch on and off. You see that? It's very straightforward. We'll see it again in a moment. You see them switching around, so we can change the rate. When we went to the field, this is what the farmer does traditionally in the red line, where they use a standard rate, let's say 75 gallons per acre. Our sensors, the blue line, this is what they're suggesting our flow rate should be, and then the dotted line is what the actual sprayer nozzles put out, because we're using a flow meter to measure the flow. So for the longest part, until we get here, we're pretty much a good fit to what the sensors see and what the output is showing. It's all based on Arduino boards. Those of you who are into electronics will know that the simplest way to make a prototype is with these $10 circuit boards that you can make. And there's huge internet discussion groups, chat rooms, about how to operate these things. So we can take all these things, flow rate, pressure, there are the sensors, put it all through this device, and then log with the data logger, which tells us what the signals are seeing, and then using a simple onboard computer, send it wirelessly to the laptop at the end of the row. And we know what's going on. Here you can see it again, close up. Can you see them going around? And then they're operated by electric valves which are opening or closing compressed air lines. The green is the compressed air line. So we're switching on and off as and when we need to change the liquid flow. But what about the air? Because this is the other fluid involved. So this is the system we've got a patent on here at Cornell, and you can see it's a simple louver. We call it the Cornell louver system. It slides, and in fact it's not just simply sliding, it's actually redirecting the air, turning it 90 degrees. So if any excess air, any air is not required, therefore it's excess, it's turned 90 degrees and comes out the back of the machine, whereas the green is where the spray is leaving the sprayer. And so early season, minimum airflow, very sparse tree, maximum at the end of season, then we want more air to penetrate the canopy, and so we can adjust it. We adjust it then by using an actuator. Here it is, an electronic actuator. Here then is the sensor. When he moves the washing up bowl nearer the sensor, so you see the actuator changes. So if density of the canopy, the signal changes, so the echo is collected, and so the actuator changes. So that was that. Again, it's the Arduino board system, same system as we've just seen, so it's very simple to repeat, and so that was okay. And our work shows when we look at deposition, which is how do we know that we've got enough spray on the leaves, you can see by changing the airflow we're getting very good deposition at lower air speeds, in fact as good as a high speed, and the high speed air creates a drift which we don't want, and therefore we're getting same deposition at much lower air speeds, which cost less money. The modern farmer, though, those that are seeing to the future, they don't really want these old-fashioned air blast sprayers. So there's quite a development towards these Sardi fans. We've done trials up in Orleans County with this type of sprayer. This grower has 4 of them, and you can see they're vertical fans. And this is what the machine is seeing. This is our estimated density signal in blue, left and right hand side of the tree, and then this is the fan regulation, and you can see the fan can react very rapidly. This is on the variety piñata, and you can see tremendous response. There's a gap in the row of trees. There's some trees missing, and you'll see that when we watch the video. And so we can regulate the fan speed. There it is. So here you can see how narrow the modern planting is of a modern orchard. And when the machine starts, it's on full bore, so it's blowing the spray right through. You see it's going to land on the grass, it'll result in pollution, and then the sensors kick in and it'll start to keep that spray just within the canopy. It's not, you see, there's just the odd wisp where there's a gap in the canopy. So it's still working. We'll move in a wee bit. Can you see? So it's still just puffing in. It's not blowing it all the way through. And this is with a modern sprayer. With the old-fashioned sprayer, it would be all over the place. So we're certainly controlling airflow. Here's the gap in the trees, and it then picks it up. So that's changing air and liquid flow. And then I'll just skip this part, if I may, because of time, and show you the boom sprayer section, because that will interest. Oh, we're nearly there anyway. There it is. So boom sprayers, what developments have occurred there? You can clearly see the first thing is boom movement. When the big sprayers go across the field, either very rough field or too fast, we're going to get boom movement, either boom bounce or boom yaw, where the booms move backwards and forwards, Y-A-W, boom yaw. And so that's a big problem. When you get boom yaw, you get acceleration of the boom. The tip of the boom moves forward rapidly, and then it lingers, and then it swings back. And you can see you've got 400% application, and then as it's moving through the horizontal plane, and you get less application. So you're getting ineffective application, even with a boom sprayer. This is work done by Van der Zande at Wageningen, and you can clearly see that when deposition is okay, we get lower infections. When deposition is not satisfactory, we get these peaks in infection here. Okay, so as the green is down, then the disease has gone up. You can see this shown in a three-dimensional model where we've got these peaks depending on the sprayer boom. What can be done about it? We can buy boom levelers. Here's one attached to the boom, and this is in the US here. And again, it's ultrasonics. So it's sending the sound wave down. It hits the wheat crop or barley, whatever our target crop is, and then it stabilizes the boom. So it will adjust the boom up and down hydraulically. Also, you've seen this. We showed you the Lechler system where we have a cluster of 3 nozzles. In this case, we have a cluster of 4 nozzles on the horizontal boom. And again, we can change the flow rate, so we can change work rate due to variation in speed. We can vary the application range for a specific area of crop, and we can switch from 2 low drift nozzles if we near the boundary of a field near a watercourse. And you can see clearly how the 4 nozzles switch in and out. And so depending on what you want where, you can flick from the cab a switch to change the different colored nozzles. Okay? And then you can have all 4 on. But that was the early days. That was, say, a decade ago. Now we've got GPS, originally giving us boom sections. As you know, the boom is in 1, 2, 3 sections on the left, 3 on the right, and 1 in the middle. So 7-section boom. And we could switch them on and off to prevent overlap on the headland. Those of you who know farming terms, the headland, around the boundary, the edge of the field. We've now moved on again, where we can not just the boom sections, the individual nozzles. And this is work done by Scott Shearer, who was at University of Kentucky and is now at the Ohio State University. And he is showing, in this case, 6.2% reduction in spray use, but he recorded up to 9% reduction. So just simple technology will allow you to save 9% your spray, because you can switch on and off, where you turn on the headland, all done through GPS and switching the valves off. Equally, changes in pressure affect, and as you know, pressure affects nozzle output. And so this is some work they did in Kentucky at Lexington to show the changing pressure across a field. With changing in pressure comes changing in output. And you can see if the nozzle is fluctuating from as low as 20 psi, you're only getting 0.3 of a gallon per minute. If you go all the way up to 100, then we're at 0.8 gallons. So any variation, as he found in this field, then is going to give us an incorrect application rate. So maybe the product won't work anymore. And then the final part, to show you what is the most modern thing, won the big silver medal at the Agritechnica show in Europe, and that is AccuSpray working to zero. One of the banes of the farmer's life is going back to refill, because it affects output, because you have to transport the vehicle, it's not in work. And so this system allows you to see what your flow rate has been, how much was in the tank to begin with, how much is left. And so if our last point, if we originally wanted to put on 100 litres per hectare, so 10 gallons per acre, and the machine says we can actually, if we use 91 litres a hectare, 9.1 gallons a hectare, we will run until we get to the end of a row. So you're not going to stop down in the middle of the field. And so it predicts when you need to refill the sprayer based on flow rate, location with GPS, and then tank contents. And so you start the system and it flags up that if you reset it automatically to 91 rather than 100, you will get to the end of your work zone. So it saves a lot of time in the amount of liquid left in the sprayer and when you refill. So you change what you want as your default. And so that's the latest system. And I'd like to leave you with this slide. And that is, in field crops, we have tremendous adoption of technology. In the Midwest states, they have auto steer, they have all these things I've just shown, or some of the things I've just shown you on the Amazon sprayer. But in horticultural crops, which is my area, we have a fear of technology. And I show this to the growers all the time. Their biggest point is the cost involved in repairing, because they're what we call nut buggers. You know, they like to spend their time trying to mend a sprayer or mend a tractor, and after so many hours they have to give up, throw their arms in the air, say, well, we failed to do that, and then still have to pay $75 an hour to get it fixed. So it's a different mindset, but the more we show them other aspects of agriculture, then hopefully they'll adopt this technology. But at the moment, it's still very early days to get them to switch. If you're excited by spraying, I commend these two excellent publications to you, where you'll see lots of our research work. Great, thank you very much.
This has been a production of Cornell University, on the web at cornell.edu.